Henkel transform of derivatives. Henkel transform of df by dx, where p is the root of the equation Jn of pa, which is equal to 0. So we know that from the definition of Henkel transformation, Hn of f of x, which is equal to integral 0 to a f of x into Jn of px dx. So Hn of df by dx, replacing f of x by df by dx, which is equal to integral 0 to a df by dx into x into Jn of px dx, which is equal to integral 0 to a x into Jn of px into df. So just we are cancelling dx in the denominator and dx in the numerator, so you will get df. So now we are using integral u dv formula. So integral u dv, which is equal to uv minus integral v du. Here u is nothing but x Jn of px and v is nothing but f, that is f of x. So uv, so x Jn of px into f of x, that is uv. So lower limit 0, upper limit a, minus integral 0 to a v f of x into derivative of u d of x into Jn of px. So applying the upper limit, so replacing x by a into Jn of pa into f of a, minus replacing x by the lower limit 0, so 0 into something 0, minus integral 0 to a f of x into d of x into Jn of px. So that is equal to, we know Jn of ph is equal to 0, where p is the root of the equation Jn of pa equal to 0. Therefore the total term becomes 0. 0 minus integral 0 to a f of x into derivative of x into Jn of px. So Hn of df by dx, which is equal to minus integral 0 to a f of x into d of x into Jn of px. That is equation number 1. Now considering derivative of x into Jn of px, that is equal to, so now we are using duv formula, right, duv, which is equal to u dv plus v du. So here u is nothing but x and v is nothing but Jn of px. U dv, x into derivative of Jn of px, that is Jn dash of px, derivative of px you will get p, right, plus keeping Jn of px as it is, u dv derivative of x is 1. So that is equal to x Jn dash of px into p plus Jn of px. That is equation number 2. We know the recurrence formulas. There are two formulas we are going to consider. So first one, 2 into Jn dash of x, which is equal to Jn minus 1 of x minus Jn plus 1 of x. That is equation number 3. And the second recurrence formula, 2n Jn of x, which is equal to x into Jn minus 1 of x plus Jn plus 1 of x. That is equation number 4. In 3 and 4, we are replacing x by px. In both recurrence formula, we are replacing x by p of x. So first one, 2 into Jn dash of px, which is equal to Jn minus 1 of px minus Jn plus 1 of px. That is, so divided both side by 2. So you will get 2 by 2 cancel in the left hand side. So you will get Jn dash of px, which is equal to 1 by 2 Jn minus 1 of px minus Jn plus 1 of px. That is equation number 5. And the second one, so 2n into Jn of px plus, which is equal to px into Jn minus 1 of px plus Jn plus 1 of px. So divided both side by 2n. So left hand side 2n in the numerator and 2n in the denominator get cancel. You will get Jn of px, which is equal to px by 2n Jn minus 1 of px plus Jn plus 1 of px. That is equation number 6. Now using 5 and 6 in equation 2, right, derivative of x Jn of px, which is equal to x into Jn dash of px into p dx plus Jn of px dx. That is equal to x into p 1 by 2 Jn minus 1 of px minus Jn plus 1 of px dx plus px by 2n Jn minus 1 of px plus Jn plus 1 of px dx. That is equal to px by 2 Jn minus 1 of px minus px by 2 jn plus 1 of px plus px by 2n jn minus 1 of px plus px by 2n jn plus 1 of px dx. That is equal to, so now we are grouping jn minus 1 of px from the first and third term. So px by 2 plus px by 2n into jn minus 1 of px dx plus we are grouping the second and fourth term, that is jn plus 1 of px is common. So we will get px by 2n minus px by 2 jn plus 1 of px dx. That is equal to, we are taking px by 2 outside, so 1 plus 1 by n into jn minus 1 of px dx plus again we are taking px by 2 outside, px by 2 into 1 by n minus 1 jn plus 1 of px dx. Taking LCM, px by 2, n is the LCM, n plus 1 by n jn minus 1 of px dx plus px by 2 taking LCM 1 minus n by n jn plus 1 of px dx. That is equal to px by 2n n plus 1 into jn minus 1 of px dx plus px by 2n 1 minus 1 jn plus 1 of px dx. Therefore d of x into jn of px, which is equal to, so px by 2n n plus 1 jn minus 1 px minus, we are taking that minus outside, minus px by 2n n minus 1 x into jn plus 1 of px dx. Here px by 2n is common, you take it outside, so px by 2n into n plus 1 jn minus 1 of px, and dx is also common, minus n minus 1 x into jn plus 1 of px into dx. That is equation number 7. Using 7 in 1, hn of df by dx, which is equal to minus integral 0 to a f of x d into x jn of px, which is equal to minus integral 0 to a f of x into p by 2n n plus 1 into x jn minus 1 of px minus n minus 1 x into jn plus 1 of px dx. We are keeping x with j, right? That is what, that is easy to write Henkel transformation, right? Whenever you are seeing the Henkel transformation definition, x with j, jn, right? Jn of px, right? That is what we are keeping, x with jn minus 1 and the next term x with jn plus 1, right? That is equal to minus p by 2n integral 0 to a f of x into n plus 1 into x jn minus 1 of px dx minus integral 0 to a f of x n minus 1 x into jn plus 1 of px dx. That is equal to p by 2n minus n plus 1. So we are multiplying with minus integral 0 to a f of x into jn minus 1 of px dx plus minus into minus plus n minus 1 into integral 0 to a f of x into jn plus 1 of px dx. Therefore Henkel transformation of df by dx, which is equal to p by 2n minus n plus 1, so whole term, that is f integral 0 to a f of x into jn minus 1 of px dx is nothing but hn minus 1 of f of x, right? From the definition, hn of f of x is nothing but integral 0 to a f of x into jn px dx, right? Here instead of jn you are having jn minus 1, that is why we are writing hn minus 1 of f of x. Similarly in the second term, plus n minus 1 hn plus 1 of f of x. Thanks.